Okay, we've been told that male head breadths follow a normal distribution with a mean of 6 inches and a standard deviation of 1 inch. And we want to test if one male's head is bigger than 6.2 inches, I believe. Oh, no, we want to test if it's less than 6.2 inches. So the first thing is one male represents one data value, and we want to know the probability that that data value is less than 6.2 inches. And if you think about, first of all, in the problem you've been told, it's a normal distribution, but just head breadths and the sizes can range from 6.0, 6.1, and everywhere in between, so it's a continuous distribution. So that backs up the normal distribution. So the first thing that I would do in solving this problem is graph what's going on, and being told that head breadths follow a normal distribution. I have a pretty bell-shaped curve, and the mean is 6, so that sits right in the middle, and then I locate 6.2 just to the right of the mean, and then finding the probability that that data value is less than 6.2, we shade in all the points that are less than 6.2, and so that's the data to the left. So my probability is going to be the corresponding area. So I'm going to need to now standardize the probability using a z-score. And so this would be the same as the probability that the z is less than, and a z-score, is x minus mu all over sigma. So my z-score is going to be 6.2 minus the mean all over 1. So this would be the same as the probability that z is less than 0.2. And then I'm going to need my calculator. Once I have the z, this is going to be normal CDF, negative infinity to 0.2, which comes out to 0.5793. So there's a 57.93% chance that a male selected at random would have a head breadth that's less than 6.2 inches.
No.
In this problem, it's very similar to the previous problem, except now we're taking a group of 100 men and calculating the average head breadth. And a lot of students think that there's not much difference between these two expressions, but there's a huge difference. This one is saying, what's the chance that one data value is less than 6.2? Over here, we're saying, what's the chance that a mean of a lot of data values is less than 6.2? That's a huge difference in that this problem is what we call a sampling distribution. And in a sampling distribution, we know that the population mean for a sampling distribution is the same as the population mean, the original population mean. But the standard deviation of the sampling distribution is going to change. It's going to change depending on how big your sample size is. It will be reduced by a fraction of the square root of your data size. So our standard deviation for the sample is no longer 1, like the original population. It's now 0.1. Okay, there's much less deviation of means than there is for the original data set. So the probability that x bar is less than 6.2, so again, because the original population is normal, the sampling distribution will be normal with the same mean. It's just skinnier now because the standard deviation is smaller, but 6.2 is still right next door to 6.0, and we're still looking for the probability that you're less than 6.2. So we're looking to the values to the left of 6.2, and we're looking at this corresponding area. So again, we have to compute our z-score, and 6.2 minus 6 all over, not 1 anymore, but 0.1. And this this comes out to the probability that Z is less than 2, which is normal CDF, negative infinity to 2, which is equal to 0.9772. So again, remember, with one man, there was a 57.93% chance that his head breadth was less than 6.2 inches, but when it comes to a mean of a sample size of 100, there's a 97.72% chance that the mean of those head sizes is less than 6.2 inches. So what if a motorcycle helmet company wanted a 95% guarantee that its helmets would fit a man's head? In this case, we're now being told our probability. We want to have a 95% chance that that helmet size is going to fit over a man's head, and so that's going to mean that our guarantee is going to be out here. We're looking for that value, and actually I'm going to call it K. We're looking for a value for which 95% of men will be below that value. So in this situation, we're given the probability. We need to get to the data value. So we've got a different scenario going on. We're being told the probability that X is less than or equal to K is equal to 0.95. And this is the scenario where we need to use the inverse norm function on our calculator, because we start with the probability, and when we plug in inverse norm 0.95, we get a z-score of 1.645. It's a special z-score. But so 1.645 is our z-score, so our data value is going to be, using the z-score formula, K. Our mean was 6, and our standard deviation is 1. So this means that our helmet size would have to be 7.645 inches to be guaranteed to fit 95% of males' heads in this population. The end.